Hello, good morning all, and once again welcome to this unique live technical discussion series. So we had interesting discussions earlier on low-rise structures, that is for wind force estimation for the low-rise structures as per IS 875 Part 3 2015. Thereafter, we had a discussion on the tall buildings, that is how to estimate wind force as per IS 875 Part 3 2015. And thereafter we decided that let's have one more session on the wind tunnel testing for the tall buildings. So today we will be having our focused discussion on the wind tunnel testing for the tall buildings. Okay, so once again, very good morning to all of you. And we will be having shortly Tony from Windtech Consultants with us. Okay, so good morning, everyone, and welcome to this live technical discussion series. Just to quickly introduce Tony, he's from the Windtech Consultants. He's having around 33 years of overall experience. He is one of the founding directors of Windtech's consultant, and his research includes reliability of wind tunnel studies, interference, excitation of tall buildings, analysis techniques to accurately determine the effects of coupled molds and rigidly linked substructures, as well as the wind noise in the buildings. And he has undertaken and supervised over 2,500 wind engineering studies, including wind tunnel investigations for various high-rise buildings, large roof and stadium building projects around the world, including many landmark projects. So it is our honor to have Tony with us for such an interesting topic. Yeah. Good morning. Good morning, Ravi Chandra. Okay, so I'll request all online participants to like and share this video so that we receive wider participation. And also, you may subscribe this channel so that you will receive the notification whenever we go live. Okay. Meanwhile, now Tony has joined, so let us welcome Tony from Windtech Consultants.
Hello, everyone. And thank you, Robin, for the introduction and for hosting this very interesting channel.
Yes.
So I'm going to share my screen now.
Yeah. So let us wait for a couple of more minutes. Few participants are still joining.
Okay.
So what we have planned in this entire talk, that we'll be having a presentation from Tony. I think it will run around 40 to 45 minutes. Okay. And thereafter we'll be taking few questions from the social media. And then whatever interesting discussion points you will be suggesting in the live discussion chat, that also will be taking it up sequentially as and when time permits. So that is the overall agenda we have today, right? Okay.
Good.
Yeah. So you can see your screen now. Yeah.
I'm going to show you the overall structure of my presentation.
Okay.
Am I sharing my screen now?
Yeah. Your screen is showing now. Now it is there on the screen.
Okay. All right. Good. Okay. So I'll just start now. Okay. All good? You can see the screen? Okay. So you can see that we want to cover a few topics today, all around the subject of wind tunnel testing for tall buildings. And the first one, which is a very important question, is when is wind tunnel testing mandatory in India? Okay. Next is some basic requirements that need to be fulfilled when undertaking a wind tunnel study. Then I'll go through a few case studies, and then I will elaborate on some different wind tunnel study techniques for the study of the dynamic response of tall building structures. and which technique is best for what type of building. Fifth topic is quite important because it does impact on the final result in a significant way, and that is how we account for the directionality in the wind climate. A sixth point would be of interest to many structural engineers who want to monitor the performance of the structure over a long time to achieve ability to see how the structural health of the structure is progressing over its life, particularly after large wind events or seismic events, although wind is more critical generally in India than seismic. Then I'll cover a couple of other areas, which is the study of wind pressures on facade cladding, which is undertaken a bit less common in India, and even less common environmental wind studies. But it's good to have a little bit of an appreciation of what can be achieved from these other studies. And then I'll provide an opportunity for some questions. I believe some questions have already come in from a number of people. So yeah, so that obviously we'll try to answer them as they come in. Okay, so starting with the first point, if we go to the Indian standard 16700 with the title Criteria for Structural Safety of Tall Concrete Buildings, this clause here, 6.2, stipulates fairly clearly that wind tunnel testing must be undertaken if the building falls within any of the following cases. So buildings taller than 150 meters, regardless of the dynamic properties or shape, buildings that have a complex geometry in plan or elevation. You're welcome to ask what that means if you like. Buildings located in a complex terrain. So if your building is, for example, sitting in moorland close to this very large hill or mountain, that the loads there would be influenced by the movement of the wind around that very large geographic or that large topographic form. Also, I'd like to congratulate the Indian Standards Committee for introducing some provision for interference excitation. This is quite important, and I believe it's the first standard in the world that addresses this issue. It is a real issue, and if your building is potentially influenced or by an upstream building of similar plan, dimension, and height or higher, then you really should be considering wind tunnel testing. Also, whenever the natural period is greater than 5 seconds, the crosswind response becomes very sensitive to the shape of the building, and the codes can't really accurately account for any small changes to building shapes, and hence the need for wind tunnel testing for that situation. Okay, so next topic is minimum requirements for a wind tunnel study. Firstly, I need to highlight what is the purpose of a wind tunnel. A wind tunnel's aim is to accurately simulate the structure of the wind as it moves over the Earth's surface. So this is one of the 3 wind tunnels at Windtech Consultants, this image here. And what is the terrain that we aim to match in the wind tunnel? It's not a simple question, because if you look at this site as an example, it is influenced by terrains from different terrains from different wind directions. In some directions, you have multiple terrains. You have a body of water, which is a very low roughness, and then you have a sort of a high roughness here, and even higher close to the site. So in the wind tunnel, we can simulate accurately. So this inner circle here is the extent of the surrounds model, which is typically about 350 to 500 meter radius from the study building. It's very important for the wind consultant to be able to convert these different terrains into a combined profile, wind speed profile, and then match this in the wind tunnel. So this needs to be done for different wind directions, and they're not, as you can see, not necessarily all the same terrain. So it's important that the different terrains are modeled for the different wind directions in the wind tunnel. Okay, if you are located next to a significant mountain or hill, then it's not, these are much larger systems and can't be modeled based on the limited size of a wind tunnel. So the solution is we do what is called a topographic study. This is a much smaller scale to be able to capture the full extent of these mountains and to see what effect they have on the local wind climate. So what we do is we then modify the local wind climate to account for the effect of these significant terrains before we do the testing in the wind tunnel at the normal scale, which is typically 1 to 300 to 1 to 4 or 500. Now in the wind tunnel, we aim to simulate some very key parameters that are in the real world. So this is the height above the Earth's surface, and this is actually the coefficient of turbulence intensity. You can see here, as we go higher above the Earth's surface, the turbulence intensity reduces, and the rate of this change in turbulence intensity depends on the upstream terrain that we are trying to model. So for this particular case, we have an open terrain, and we're trying to simulate that in the wind tunnel. So you can see the triangles is the wind tunnel recordings against the benchmark value, which is the blue. And the wind speed, the mean wind speed, also picks up with height, so different to turbulence. And that also needs to be matched in the wind tunnel. Okay, and these need to be matched to within 10%. Okay, so if we take a spectrum of the wind speed, this allows us to check a third important parameter, and that is where the peak of this spectrum lies, and that peak then tells us a lot of information. It tells us about the size of the eddies in the wind tunnel and how they match with the full scale. So the green line represents the best fit to our wind tunnel data. The red is the target spectrum, and you can see there's a bit of an offset. And in this situation, we have the target length scale is 337 meters. In the wind tunnel, we have 195, and that's a factor of less than 2. So the target is to make sure these are not out by more than a factor of 3. Okay, the other important factor is the accuracy of the surrounds, the accuracy of the study model, and if there are any topographic features within close proximity, they should also be modeled. You can see this example here. Another important parameter is that the cross-section of the entire wind tunnel model, including the proximity model, should not exceed 10% of the wind tunnel cross-sectional area. The reason for that is if it becomes much bigger than that, it will start to the blockage will start to influence our results. There will be a speed up at the test location, which would unnecessarily exaggerate the forces and pressures and speeds around the study model. Now, you'll see in the ceiling section here a very interesting detail, and this is called a blockage tolerant test section. So this is in one of our 3 wind tunnels. We have this feature which allows us to accommodate more than your typical 10% blockage because of the ability of these carefully designed slats to release some of the build-up of pressure at the test section due to large blockage. When the blockage is not large, it behaves like a sealed ceiling. Okay, so in this situation, we can manage a blockage of up to 17% of the cross section, although we really do need to test scales that require this. Another important parameter is to have the model large enough, so which is the opposite of what I just mentioned. So there is a balance between having the model small enough so it doesn't cause blockage, but also needs to be large enough so that it creates an accurate simulation of the flow regime around the building. Okay, and the wind speed needs to be high enough. So this combination of wind speed and dimension, which is model dimension B, and mean wind speed in the wind tunnel U, and that's at building height H, this divided by the viscosity constant of air is called the Reynolds number. So it's a very easy calculation, and any engineer could easily check the Reynolds number of the wind tunnel setup. And a very important parameter is that this number must be greater than 50,000 for any cross section in plan, for any plan shape. For circular planes in particular, these are more sensitive to Reynolds number, and they would generally require a higher number than 50,000. Okay, and typically we recommend greater than 800,000. Okay, so these need sort of fairly carefully planned experiments to ensure we get this much higher Reynolds number. So what are the outputs we expect from a wind tunnel study? Well, at Windtech, part of a standard deliverable is to show you the headline overall base moments in a comparative form against a number of other standards, including the Indian standard, IS 875, about X max peak, about Y peak, most moment, and torsion. And we compare that just so you can get a perspective of where we're sitting with respect to various standards, not just the Indian standard. It also gives you an idea of the variability amongst the different standards as well. We also provide a set of load cases in the form of point loads to be applied at certain specified location on each plan of the building and each level, on each floor of the building. And these are examples of 2 load cases. Typically, we provide 32 load cases to be applied to the structural engineer's FEA model. We also, as a standard, provide a detailed sensitivity analysis. And in this example, this circle represents the dynamic properties as supplied to us and this is a mode, the natural frequency of a particular mode of vibration. This tells us what happens with a plus 10% or minus 10%. These parallel lines here, almost parallel, tell us how sensitive this load is to changes in the mass of the building. And if you move across here, you can see the effective change in period. Okay. At the same time, you can see in this example, which is presented for accelerations with 1% inherent structural damping, the target criteria. So in this particular example, you can see the target criteria for a residential and also for an office building, which is less stringent. This is for a 1-year return. So we give you this plot for different assumptions for inherent damping as well. Now we move on to a third topic, which is a number of case studies, some interesting case studies, and some of the lessons that we can learn from these examples. So you could see here, this is an interesting building in Australia. It's still currently the tallest building built. It's called Q1 Tower. This tower, it's got a sharp nose, you can see here, which is pointing towards the prevailing wind. And it's a very aerodynamically shaped with respect to the prevailing wind. So in surface paradise, the wind is very predominantly from the southeast direction. So in addition, you can see some stepping in plan as you go up. These two features make this building form a very efficient building in terms of aerodynamics, and loads were relatively low for a building of this height. And I'm seeing results for buildings shorter than that in the Gold Coast that are proposed, that are about 50% higher in terms of base moments. So it just gives you a bit of an idea how shaping a building for aerodynamics makes a big difference to the overall cost of the project. Also, we didn't have any issue at all with accelerations. There was no need for a damper, etc. And as you know, buildings that are not aerodynamically shaped and of that sort of height would most definitely require some form of damper. This is another example here. This is Ocean Heights in Dubai, which is in Dubai Marina. One of the first very tall buildings to be built there. This tower has a 60-degree twist over the height of the building. A twist in the building plan tends to be very effective also in reducing the dynamic crosswind response. And again, we found these two towers are of a similar height. We found, just slightly lower loads, a few percent lower compared to this one, perhaps because of the twist for the same basic wind speed. Okay, tapering is also very efficient. If you combine tapering with a corner treatment, you can easily achieve a 50% reduction in the response in the crosswind. When I say crosswind, you may think, well, why are we worried about crosswind? Yes, once you get buildings of this sort of heights, the design is invariably dominated by the crosswind response, not the along wind. And if you're able to bring the crosswind response down by 50%, that could be essentially a 50% reduction in the design loads. And you can imagine the cost benefits that could be achieved from that. Okay, this is another interesting example. These buildings look relatively flimsy, just if you look at them as individual buildings, but they are not actually individual buildings. They are actually connected rigidly at these elevated points. This rigid connection suddenly makes a very big difference to the aerodynamic efficiency and stability of these buildings. And we tend to see this very often. So Windtech have developed what is still considered the state-of-the-art analysis method for accounting for this linkage between substructures. So we call each of these towers a substructure of the total structure. And this is largely because when the peak load occurs on one of these substructures, it hardly happens simultaneously with the other one. So what happens, the other one acts as a buttress to stabilize its mate, if you like, that it's connected to. So we tend to see significantly reduced overall dynamic responses because of the fact that you're getting much larger generalized mass for being engaged for a lower peak response. Okay, this is an interesting, very slender tower in Kolkata, and you can see there's apart from a little bit of a corner treatment here, we're not seeing any tapering, etc. As a result, we had an acceleration exceedance here in this building, and the solution was a very simple and cost-effective damper design, which was implemented near the top of the building in the form of these two stacked tanks. These tanks could also double up as a fire hydrant tank for the building. Yeah, so that's essentially a very simple, cost-effective. If you factor in that this building would have had a fire hydrant tank anyway, then the cost is almost negligible for a damper. Now, if you speak to other wind consultants, I know at least one, you would find that they would want to be pushing multi-million-dollar solutions, which would not be as even more effective than this. Keep in mind that this system is able to resist or mitigate accelerations in both X and Y sway modes simultaneously. It's a very clever system, very cost-effective to achieve that kind of result in systems such as a tube mass damper or hummingbird or whatever. You would be paying, 5-6 times as much and not achieve, at least for the weight, not much better outcome. Okay, so this is an example of a project in Mulund in Mumbai. You could see here that there are a lot of taps on there. So we used a technique called the pressure integration method, and what we found is the end tower experienced somewhat higher base moments because of the wind tend sort of to accelerate around the end compared to the other towers. Okay, so just keep in mind if you're doing a project where you have sort of continuous wall like this, that this can create larger loads at the end tower, more perhaps sometimes slightly higher than what would be predicted in the code. The code's not designed for these kinds of arrangements. It's designed for an isolated building. Okay, these are some other examples of tall buildings that we've worked on. Now, this is definitely beyond the scope of a wind code, a building of this complexity. So this is actually a reinforced concrete core with a steel frame structure, and I believe it was a copper cladding. So designed by skeleton structural engineers. So this was actually tested using both the pressure integration method and the force balance, and we found very good agreement between the two methods for this such a complex building, which shows tells us. So this is a statue of Lord Shiva in central India, and it sort of demonstrates that the capability of the pressure integration method, which we generally prefer over the force balance method. So the force balance is you put basically a force balance inside the model, and then it measures directly the shear and bending X, Y, and torsion. Pressure integration, you put pressure taps all over the model, and then they're measured simultaneously with no phase lag between them, and you can get exactly the same overall moments. But the advantage with this method is you have a much better idea on how to distribute the mean part of the response over height, which for a structure like this could be a challenge. Now you'll notice there's the Trident here. This snake here is not a structural connection to the building, so they were concerned about the dynamic behavior of this Trident. So if you recall, we would have an issue with Reynolds number here, because we have wind speed and dimension. So the dimension here doesn't satisfy the Reynolds number requirement for accuracy of flow regime. For that reason, we needed to model that Trident at a larger scale, not ignoring the influence of the rest of the statue on the forces on this Trident head. So it's very important not to ignore very important modeling parameters such as Reynolds number in your wind tunnel studies. Very important as a structural practitioner that you recognize these very important parameters for accuracy. So you can see here, in addition to the structural response, we are able to provide the maximum peak pressure on the cladding and the minimum pressure distribution. And these are global. So basically for each point there, we look at the effect of 36 wind directions, and you get the largest discretized peak value at each point, and that becomes a design value for cladding. Unlike structural response, obviously, we look at the overall contribution of the pressure distribution on the load effects. Okay. Now, this takes us now to the fourth topic, which is the different methods that are utilized for study of wind forces on buildings. So I'm going to need to speed up a little bit because to make up time. So this model here, you can see, is attached to a force balance. You can see these concealed connection points, and this is one method. Pressure integration is another method. Let me just go back one step. Pressure integration, which I discussed earlier. Aeroelastic model. This is actually a dynamic model. Okay, and there's the full aeroelastic, where you have a super tall building more than, say, 500 meters in height, or we're talking about perhaps even more than 600, where you can get some significant contribution from the higher order modes on the overall load effects. Okay, so basic minimum requirements. So if you want to know more about this, I encourage you to go to the awees.org website and download for free a quality assurance manual, the 2019 edition, okay, which I was a main author, and it spells out in simple but detailed way what are the important key parameters. Okay, so So I'm not going to bore you with these details. I suggest you have a read of that document. So one of the requirements is if it's a force balance, the model needs to be light enough and rigid enough, okay, so that its own natural frequency is much higher than our target or the range of frequencies that we are interested in the load spectrum. Okay, this is an important consideration, particularly with a force balance model. Okay, so this is an example of the 36 load spectra that you get from the wind tunnel results. This spike here is actually due to the study model. So you want to keep away from that. You're going to make sure that the range of actual reduced velocities, that range here, needs to be clearly distant from our model frequency. Now, pressure integration, some basic requirements. You need to have a very good pressure measurement system that can capture the pressure with no phase lag between any of the points, and a sufficiently dense layout of pressure taps. And this is one of the key parameters here. Okay. Aeroelastic models. You need the model needs to be able to have a natural frequency in the two translational modes in the same ratio as the full scale, okay, to within 5%. So if your second mode is sway about y of say 0.3 hertz and the first mode is 0.2 hertz, then that 1.5 ratio needs to be replicated in the model. Okay, so other important, the next most important would be the mass of the model itself. It needs to have the same structural density as the prototype building. Okay, so these are two most critical. Also, the damping, the inherent damping in the model needs to also match the inherent damping in the prototype building. So I'm going to cover in a minute which types of buildings is this particularly important. Okay, the answer to that is when you have a reduced velocity greater than 8. A reduced velocity is the mean wind speed at building height divided by the natural frequency of the first mode of vibration, and also in the denominator the characteristic width, which is the narrowest overall width of the building. For particularly if the building is steps, then it'll be the narrowest overall width in the top half. Okay, or you can take average in the top third of the building. Okay. So this doesn't happen very often. It happens if the building is particularly high, so you get a very large mean design wind speed at building height. If it's very slender, then you have a very small b, so that also tends to push up the reduced velocity. Okay. So this is for the vast majority of buildings that would fall under this category. If your building happens to be hexagonal, octagonal, then the phenomenon that requires this type of study, which is we call aerodynamic damping, starts to kick in at a lower reduced velocity of around 6. For circular or elliptical buildings, it starts from a 4, which is why you don't see many super tall buildings with a circular or elliptical plane. But for 95% of cases, you wouldn't need to go to the extent of an aeroelastic model. We always, when approached by a client looking to do wind tunnel study, we always check this parameter and advise them that below what natural frequency will their building start to require this type of study. So this is an example of a tall building in Bangkok, and you can see how the building is oscillating in the wind. So all of the sway modes are replicated correctly, damping mass. What we do at Windtech is the Aeroelastic model doesn't necessarily replace a force balance or pressure integration. It's done in addition. And we overlay the two results. And you can see here the Aeroelastic results show some increase, in which we call negative aerodynamic damping. So it actually, the aerodynamic damping is negative, means it subtracts from the inherent damping, so you get a lower overall system damping and hence the increased amplitude. But it rarely happens in the critical angles of attack. So here, no effect. Okay. For a square-shaped building, circular, hexagonal, it could actually occur in the critical angle of attack. And for the other axis, you could see there's actually a positive aerodynamic damping. So it's actually made an overall reduction to the response of the building here. Okay, so I think we've covered this. We'll skip this. So this is a case study here, an example. For this particular building here, this building in Melbourne, Sydney. You can see that building was subject to positive aerodynamic damping. It's sort of like a square uniform plane shape. And you can see that there's roughly a 20% reduction in the ultimate base moments, and even bigger reduction for the 10-year return, also in this case 25-year return deflections. Okay. This is for one axis. For the other axis, which is the about or along the longer side, we didn't see much of a change. Okay, some slight increase here, but not from the critical angle of attack, as we saw in the other example. Now, this is an interesting example of a tall building where the incorrect, well, actually, it's interesting because we tendered for this particular project and the tender brief was correct. The tender brief correctly specified an aeroelastic study to be undertaken for this building. But the winning wind lab ended up winning on price. We found out later why they won on prices, because they actually cut out the aeroelastic scope from their tender. As a result, loads were overstated, and there was quite a lot of difficulty experienced by the structural consultant in making this building to take the load specified from this particular wind tunnel study. And shortly afterwards, this project was put on the market. One other thing that we could offer, or Windtech can offer to our clients, is a performance-based wind design approach. This is achieved through the way we incorporate the directionality in the wind climate, but also we can offer, if the structural consultant is able to set up a transient dynamic model of the structure, we can provide them a time series that they can input rather than a fixed static load. And the benefit of that, so this would be the about X, about Y, about Z for a particular load case, and that would obviously vary over the height of the building at different points of the height. The benefit of that is, if you look at this blue line, that's the typical load ellipse for a particular wind direction, from a typical scope that any wind consultant would undertake, and that's using spectral analysis. With a time domain analysis, you can see here that there could be some benefit or further efficiencies achieved due to asymmetric loading, as you can see, which can be picked up from a time domain analysis. So that's the red line gives you the time series response of XY. Okay, so I'm going to skip this next section because I think I'm running out of time here. So we'll try to cover this in a different presentation perhaps, but this covers why it's important to analyze in particular way the effective directionality. So this is just in a nutshell, shows you that the most commonly used method of in the wind tunnel versus a more rigorous method that we use here at Windtech against a benchmark. So the symbol here is basically called the storm passage method or load effect method. It lines up very closely with Windtech's multi-sector analysis technique, which is the blue continuous line. You can see how the loads can vary against other simpler methods employed by other wind consultants, such as the sector method in this case, for the base moments. So what comes out of the wind tunnel is quite, if you follow the quality assurance manual requirements, you'll get very similar answers, but it's also very important to be aware of what is being done to these aerodynamic coefficients to arrive at your design pressure or design base moments. So this is a scatter plot. So this is not just for one pressure point. Now we're actually putting a whole scatter plot of all of the pressures on the building between the benchmark direct method. You can see the multi-sector method lines up quite well. So if anything on these dashed lines means they match exactly. And you can see here with the simpler analysis techniques of the wind tunnel results, you can actually get on average about 14% conservative numbers. So instead of say for example a 2 kPa pressure, here you get actually a 2.3%, 2.3 kPa. Okay, on-site measurements of dynamic properties, that's something that we can offer if you're interested. Also long-term monitoring. We use very sophisticated hardware that we've actually built in-house using some leading sensors. We're measuring in micro G, so you imagine the sensitivity we can achieve with that. And these systems are tested rigorously in our facility using simulated building motion before we actually send them off to the site. This is an example of an installation done in Jakarta. These are some of the outputs of this typical time trace. Our monitoring system can also then convert that or derive from that the natural frequencies X, Y, and Z, and you can monitor these over time. And then after a significant event, you can see if any of these have shifted. If they have, then that triggers potential investigation to where the failure has occurred in the structure, allowing the structural engineer to identify and mitigate. Okay, so I'm going to skip this. So this is some full scale against wind tunnel comparison. The scattered results symbols represent the full scale measurements, which tend to have a bit of a scatter against the solid line. This is the maximum pressure coefficients on the building mid wall. You can see the mean, minimum, maximum pressures for different angles of attack. And this is roof corner, very particularly challenging part of the building to get close to full scale. We are able to do that at Windtech. Why? There's a very long story behind how we achieve that. One of them is to measure the pneumatic response or admittance of the tubing system itself and correct for that. We low pass filter beyond a certain point, we make sure there's not too much noise in our system. So this is not from our equipment. Our equipment doesn't have that much noise, but this is just to illustrate what could happen if it does have noise. Also, how fast we are sampling, the number of dots per second is very important to map the target signal, which is the red or orange line in this example. Okay, so I'm going to skip that. And so this is typical output you can get from a pressure study. So you get this is a contour, this is New York, sorry, about the symbol, so you have here basically able to identify the hotspots. These red zones typically in the code will be applied generally across a much larger area in the building. So this allows you to gain some cost benefits by designing for the area where they actually do occur, and rather than everywhere in the building. In fact, these numbers themselves are a bit lower than all of the corner positions in the on the building. So the significant cost benefits can be achieved from a cladding pressure study. Wind environment study is very important, particularly if you want to ensure comfortable conditions and safe conditions, more importantly, on all balconies, not just for pedestrians, not just for occupants being able to keep themselves from falling under strong winds, but to ensure lightweight furniture doesn't end up flying off and hurting some people on the street, which can happen. Okay, so these have big impacts on the community. So we have had a number of developers, such as Lodher and others, who have insisted on undertaking these studies in India. So we'd like to see more people consider these effects. In Australia, this is a mandatory requirement for every single new development. And depending on where you are, the height, once the height exceeds anywhere between 6 levels or 15 levels, wind tunnel testing is mandatory for this. Okay, so at this point, I will stop talking and allow for questions. I'll hand over now to Bhavan.
Yeah, thanks, Tony, for excellent presentation. So you covered from basics to very detailed about the wind tunnel testing, and I'm sure there are many interesting questions which will be coming out now. So firstly, can we do that? We have received a few interesting questions from the social media. So let us take them one by one, and thereafter we'll be taking a few interesting questions which are already popping up in the live chat. Yeah. So one of the question we received, like, what are the materials which are being used for creating the model in the wind tunnel test, and how it could affect the results?
Okay, so it depends on the type of study.
Yeah.
So if we are modeling a bridge, depending if you're doing a section model of a bridge, there's usually an aluminium section spine, and then we have either balsa wood or foam body over the spine. If we're testing a force balance model, some wind consultants use a foam model over fitted on a shaft like a glove. At Windtech, we use a 3D printed model using a very high or very rigid type of resin to get the high natural frequencies that you need for that's very important to be. This question is particularly important for example, dynamic models, okay, or a force balance. If you're doing a force balance, as I mentioned earlier in the presentation, your model needs to be quite rigid so you don't interfere with the zone in the spectrum that you are trying to derive your response from.
Okay.
Any other questions?
Yeah, I think you have covered this question, but the question was like, what could be the appropriate range of the scaling for the model?
Oh, okay. Yes. All right. So the range of scale needs to be balanced between the need to keep the blockage below 10%
Okay.
and to have a large enough model so you have a good Reynolds number, a large Reynolds number. So you want to make it as large as possible, obviously.
Yes.
But if you make it too large, you won't. Two problems could happen. Your surrounds, you have a fixed width. Most wind tunnels are about sort of 2-3 meters. We're actually quite lucky. We have a 3-meter wide test section in our wind tunnel, in each of our 3 wind tunnels. But if you make the scale too large, you can't take in, your minimum 300-meter extent of surrounds, which is important. The surrounds model is very important to be able to capture wind effects such as funneling from other buildings towards your site, wake from another building that can create an interference excitation that could amplify the response. You can get amplifications up to 50% in some cases, just due to the wake from another significant building. But this doesn't happen in all cases. So if you're situated near the coast, you're more likely to get that. If there's another building upstream, if it's right on the coast, I mean, if you're a kilometre or more in the middle of tall buildings in Mumbai, for example, you're less likely to have this problem. But the surround model needs to have a minimum extent.
Right.
Okay. And if you make it too large, another problem is the blockage. So your blockage starts to become very high. Okay. So I would highly recommend, if you're sending a brief to a wind consultant, do not stipulate the scale. Okay. Because sometimes it can limit. The wind consultant likes to use what is the best for each particular project. If you have a building that's like a pencil building, 6 meter wide, you don't say 1 to 400 scale, okay? Because it'll be ridiculously small in the wind tunnel. You won't get the right flow.
Right.
Okay.
Right. Another interesting question was like in India, there is no specific code for the wind tunnel testing. So in few projects, ASC 49 is followed. So can we follow other codes as we calculate the wind force as a baseline as per Indian standard code? So is it appropriate to follow ASC 49? That was the question. So if you can light on this,
All right. So first of all, I would like to say, yes, there is a requirement for this document here is also a good one. So as a guideline for wind tunnel testing, and it gives you sort of a slightly more practical outline of what are the sort of physical requirements you need to be able to get the right setup in the wind tunnel. Okay, so if you are looking for that kind of information, that's the best place to go. If you are looking at codes generally, just to design to a code, then what you should do is stay with the Indian code, because it's actually a very, very good code. In fact, it's, in my view, it's far better than the ASCE 716. Okay, it has a lot. It at least gives you a good treatment for crosswind response. We tend to find it actually goes in quite well for against our wind tunnel results in general. Obviously, within the constraints that have been stipulated in the Indian standard, as I presented earlier at the start of my presentation.
Right. Okay, one more question we have received, like if wind tunnel test results indicate that the wind force are to be increased by 10% for, let's say, for the across wind, then is it also required to along wind forces also?
No, not necessarily, because the crosswind behaves in a very different way to a long wind. okay, you can get, it's very shape dependent, okay. So you can get a building with the same along wind response, same width, but twice the crosswind response. It's not just the fact that the crosswind has increased by 10% doesn't necessarily mean you need to increase the torsion and the along wind. No, absolutely not. However, they are obviously, as long as you are mindful of the minimum loads stipulated in the Indian code, which is IS 16700, says you can't go below 70% of the code value. Okay, so as long as if you need to bump up one by more than the other to get to the minimum 70%, then that's obviously that's the Indian code's requirements.
Yes. Yeah, this was also interesting question. That can you please some very quick tips for interpretation of wind tunnel test results, and what could be maybe the parameters on which the focus should be given when we are looking to the wind tunnel test reports?
Sure. Okay. I'm going to share my screen.
Okay.
Let me just see if I can do that now. Can you see my screen?
Yes. Yes, we can see now.
Okay. All right. So, Barbin sent me this similar question earlier, and I have done a summary here. These are very simple points to check. Okay. First of all, you need to know what was the assumed wind climate for the wind tunnel study. For any structural engineer, do not let the structural engineer give you results without clearly laying out what their assumption is with the wind climate, whether it's to the ultimate loads or the accelerations. Equally important to know what wind speed was assumed for the accelerations. You have a right to know this. You have a right to question them if it's significantly different to the Indian standard. Okay, because ultimately you are the ultimate person responsible for the design. Okay, so this is a very important one. The proximity model needs to be extensive enough. I would say at least 350 meter radius. Check the blockage. You can tell that by looking at the photos. You can, if you sense that you've seen some of the models I've shown, like sort of zoomed out. This is a zoomed in view, so you can't tell, but if most laboratories need to show a zoomed out view. And if you sense that there's likely to be more than 10% blockage, you need to question that with the laboratory, because that would indicate there's a overstating of the loads and pressures potentially. Also, this is not really a check as much as something that should be part of the tender brief, and that is if this is a staged development and you're planning to stage it over more than 1 year between each stage, it's very important that the wind tunnel lab undertakes testing for more than one different surrounds case. One for the scenario where we know what the surrounds will be at the time of completion or near completion, and then you do a future surrounds for the future stages. Or if the site is located adjacent to another development precinct, you need to include that as a future surrounds. Okay, unless that development is more advanced than your project, then you can treat it as part of the existing surrounds. Okay, so very important because these can have a big impact. Also, it's sort of come to my attention that some wind tunnel labs test very few wind directions, and that is dangerous. So you need to make sure that at least 36 wind directions have been tested, 10-degree increments for both structural and for pressure. Not necessarily for wind environment, because the gradient in the wind speed with direction is not as dramatic as you could potentially get with dynamic response or pressure. You can get very big changes over 10 degrees. It needs to be captured with the 36 directions. And finally, which is a topic I sort of moved through quickly, but you need to have at least some idea what or how the wind consultant accounted for the directionality of the wind. Some wind consultants just totally brush this topic aside, assume they go with the Indian code, say for Mumbai 44 meters per second, and they assume that for every wind direction. And you end up having to design for a load that's far, far more than what it should be. And you end up, your client will end up paying a very costly price for a fairly cheap and nasty study. So you need to understand what was the method, what was the allowance for directionality in the wind climate, and what method was used. So there are three main methods that are currently used. One is the sector method. Now within the sector method is very similar to the code. You take different angle of attack and you see which gives you the largest load effect. Okay, so it's a much simpler method, but then they need to have done their homework in terms of the climate analysis, not just assume the same speed in all directions. Okay, so that's one. And then there's another one is an outcrossing method. Outcrossing method is a bit more rigorous, but usually what we found when we peer review this particular method is we find the accelerations are significantly overstated. So you would very likely get a recommendation for a damper at the end of this study, where it's very likely that you won't be needing a damper. So just be aware if the method involves the outcrossing method, and there's somewhere in the report says you need a damper, that should immediately ring alarm bells, and you need to come to us to investigate this in some more detail and advise you where to go from there. And then another method, which is the most rigorous method, and that is the multi-sector analysis technique, and that pretty much has virtually no error margin in it. Okay, it's the most computation intensive of the three methods, but that is the method that people are trying to work towards these days. We've been using it for over a decade here at Windtech. Okay, so also I highly recommend you go to aws.org and download for free this document here. Have a read of it. It's not a very heavy document. Most people will be able to understand it. Most structure is designed for the structural engineers to read and understand. Okay, and you can actually, to give yourself peace of mind, you should reference this when sending out tenders for wind engineering, that all testing needs to comply with AWES QAM 2019. Okay, and that would give you a lot of peace of mind.
Right.
And another couple of points which are not covered by the AWES QAM, but this is just based on our sort of a good understanding of the building life body aerodynamics. If you look at this plot of the coefficient, sorry about the label here, didn't come out well, but that's the wind direction in 50 degree increments, okay, from 0 to 350. 0 is north, and these are the base moment coefficients. So these are translational moments, okay, and this is the mean coefficient, maximum and minimum. Now, you should be able to be provided this in any structural load study report. You need to have the base moment coefficients for the translational and the torsion. Okay, you need to have a look at the mean. Okay, this is an example of a case where we found pretty much very close to the maximum mean coefficient you would expect. So in most buildings you'd be around a 0.5 plus or minus, so you got plus or minus 0.5 or 0.6. Here we've got about 0.67. That's really about the highest you would expect. But you should not see much higher than that. If you see higher than that, you know there's something wrong with the wind tunnel setup. Okay, so that's one check, very simple check you can do. For torsion, that the mean coefficient for torsion should not go beyond plus or minus 0.1 in the coefficient. Can you see those? So you can see this is the mean torsion coefficient. Remember, it's a coefficient, okay? And the coefficient is defined relative to the height. It's normalized by the height of the building and usually the longer horizontal dimension, okay? So based on that, you should not, this red line here, or orange, should not go beyond the plus or minus 0.1. If it does, there must be a very good reason. Usually there isn't a good reason, actually. All right, so that's a rule, a good rule of thumb for the average structural engineer.
Yeah. Okay.
Any other questions?
Yeah, this is an interesting question. Like in the initial presentation, we have discussed that wind tunnel testing is required, let us say, for height more than 150 meters, right?
Yeah.
So now this question is like, let us say if we have buildings which is lesser than 150-meter height, and if wind tunnel testing is done to help to achieve better structural efficiency in terms of cost or to do the current codes factor in the desired parameters. Yeah, so this was the point from.
Yes. This is done very often, actually.
Yeah.
In India as well, we have done many buildings in height range, typically from about 90 to 150. That's very common. We do a lot above 150, of course, but we tend to see very good efficiencies. Nearly every time they can gain the 30% saving on the structural load as a result.
Yeah, one more question from Atul is that, is the wind considered to be in any particular direction, or does building orientation also play a major role?
Okay, so the question, so I understand the orientation, the importance of the building orientation with respect to the wind. Yes, right. As I mentioned, with the Q1 tower and the Gold Coast. Yes, if you orient your building, depending obviously on its shape, you would get a lot of benefit. So we're at Windtech very happy to have this dialogue with the architects early on in the piece to help give them some guidance on how shaping can make a very big difference before the concept design has been locked in. And that's usually the best time to get the most out of the wind consultant, actually.
Right. Okay. One more question from Bakar Sheikh, that does the wind tunnel setup includes wind interference effect of buildings which are closely spaced to each other?
Yes. So the interference effects are depending, yes, the spacing of the buildings has a big impact on interference, and the more closely spaced the buildings are, the less the effect of interference. Okay. But if you have a 300-meter high tower, it's not likely that it'll be surrounded by 300-meter towers everywhere. So if you only need one other 300-meter tower, somewhere within 300 or 400 meters from the site, and you can get some very interesting interference effects. So just be aware of that. If your tower is relatively similar to a dense population of towers around you, you don't have to worry about interference. However, if you're sort of the next block near the coast, and there's another building, only one building or two upstream, just beware, because there could be some significant interference. So it depends on how much you're standing out amongst the crowd of towers, with respect to the wind, okay? Because you only need one wind direction where you're actually not shielded by a large number of other buildings.
Right. Okay, there is an interesting question from Bhushan. What is asking that is there a frequency analysis using wind time series excitation? So he is correlating it with the, I think, with the seismic excitation, wherein let us say we have a kind of a
Yes.
ground.
Yeah, we do. Okay, we do obtain a load spectrum. We get a force spectrum, etc., and that's how we analyze the response of tall buildings. If you're using a force balance or a pressure integration method, as I explained earlier, the main outputs from these are a spectrum we can get for each of the 36 directions that we measure, and then we overlay the dynamic properties of the building within those spectra to get the response. So it's similar in that regard. And as I pointed out, we can go a step further for those who are really keen. We can look at the time domain analysis if required. But that's very, very, very rarely done. Not many structural engineers anywhere go to a time domain analysis. This is a relatively new area for structural engineers. I think in earthquake it's more common. But for wind, we can do it. We have the capability if you need to do that.
Okay, one more question he has mentioned that which softwares are used to model these structures, specifically the wind?
All right, from our experience, I would say more than 95%, probably 98% people use software called ETABS. Okay, you're talking about the software used by the structural engineers, or
I think his question is it's not even clear to me also. Let me read out again. Which software are used to model these structures, specifically the wind? So I think
well, you can actually get ETABS does come with a wind model to give you at least a starting point. At Windtech, if we come on board, we give you a desktop study right at the beginning with some load cases just to get you started. That's usually a lot better than what ETABS gives you. And it's based on our experience. We wouldn't do it unless a wind tunnel study is being undertaken. Otherwise, it's too much liability for us. So, we tend to come in generally within about 10% of the wind tunnel results. But in most cases, we're quite close. So that's a service that we offer for no extra charge to all our clients. Once we come on board for a structural load study.
Okay, yeah. One more question, like given a chance, what would be your preference for the material selection, whether it should be ductile or rigid for resisting the wind load?
What was the first option? Rigid or what?
Yeah, rigid or ductile. That is a flexible. So whether
ductile. Okay, I think I know what the question's asking. My advice is when designing for wind, it's not like earthquake design. With earthquake, you need a ductile structural system. Okay. My advice is to stay within the elastic limit when designing for wind. The reason is earthquakes only last for 1 minute tops. Okay. For wind, you have a windstorm typically can go for even an hour or even more than an hour. If we design for ductility in that environment, there will be very serious issues with regards to fatigue, failures, etc., which is a very dangerous proposition. Some people may, if you talk to certain wind consultants, they may be trying to push for what they regard as performance-based designers to go into ductility mode. I think you should be very careful from that, because first of all, you're not getting any additional efficiency by doing that, because once the building goes into a ductile mode, its natural frequency will drop dramatically. A drop in natural frequency for wind has the opposite effect to earthquakes. Okay, it actually increases, causes a significant step increase in the wind dynamic response. Okay, the opposite. Don't think like earthquakes. Okay, if your design is governed by wind, my advice is stay in the elastic range. Don't go past the elastic range for ultimate design.
Right, and that is the overall design philosophy in the different Indian standards. That for wind engineering, structure should be
Right.
within the elastic range. Right. Yeah, Sagar has put up one very interesting point. Sir, does future high-rise construction near building considered for its effect on building? So now I think what he's trying to say that, let's say my structure is constructed at that time. Now it is not known whether high-rise will be constructed within locality or not. But let us say it is expected. Now whether
Yeah.
that effect should be considered, or how we should proceed for the design.
My advice is have a dialogue with the developer, because they know more than any of us what's
Mhm.
like to happen in the future. It could be
Yes.
just a big warehouse next door, or it could be some slum area or something. But you know, based on the site location, that this is not going to be the case for another 20 or 30 years. In 30 years' time, it could be quite different. My advice is you let us at Windtech make a postulation as to what massing could occur and test that as a hypothetical future case. It's better than ignoring this problem altogether.
Yes.
And we've done this before.
Yeah. Professor Mayank Ghoshal has asked an interesting question, that how winds are generated in the tunnel, either through fans or by other means.
Oh yeah, we use very large fans. Yeah,
Yeah.
so we have our own substation.
Ah,
So we use a lot of energy to keep
okay.
the wind going. Yeah.
Mm, mm. Okay. Okay. Bhushan has put up one more point, that how are facades protected from very strong influencing winds?
Sorry, how are what protected? Who is what?
Facades. So he's talking about facades,
Oh,
or
hold on.
say
Let me
exterior
just
parts of the building. Yeah.
look at the question. Sorry, I'm not seeing the question. Oh, facades. Okay.
Facade.
Yeah. Okay. So if you are in an area such as Kolkata, where you are likely to get a significant storm, like, for example, recently we had Cyclone Ampang came and crossed Kolkata. Okay. So these cyclones tend to generate a lot of debris. And it's very important that at least the bottom 25 meters of the building is designed to be impact resistant. Use a type of impact resistant glass if you are in that if a region that's affected by cyclones. But other than that, I think if you have accurate wind loads and you have accounted for the effect of the surrounds, you've looked at the future scenario, then you have the best protection in terms of design for your facade, because you've accounted for all of the potential anomalies that may not be fully covered in the code. So we've seen zones where you're getting the area of the highest pressure zone extend beyond where the code stipulates to be the extent of the high pressure zone. And it could be just somewhere near the bottom corner of the tower. But the fact that you're able to pick that up from a localized model study provides a lot more peace of mind And so so the simple answer is, wind tunnel testing is a good protection because it allows you to cover, especially if your building is such an unusual shape or is located within a fairly unusual building topography. Okay, does that answer the question?
Yeah, yeah, okay. Like that's a great answer. Okay, okay. This is the, I think, last question what we have received. This from Raksha Bhatia. Now, and she's talking about the oblique wind force. So, what she's telling that, do you recommend we should design the rectangular industrial shades for the oblique coefficients? So, presently, Indian Standard Code IS 875 does not give any force coefficient for say 45
Mm.
degree. But there are certain other references which are talking about the wind force at a 45 degree. So, what is your opinion about this?
Yeah, look, I think that's a good question,
Hmm.
and I think a strategy should go over and beyond the minimum requirements in the code. The code is there as a minimum requirement. It's
Hmm.
not the maximum. Okay,
Hmm. Hmm.
a good structural engineer should do their own due diligence over and beyond the
Hmm.
code requirements.
Hmm. Hmm. Yeah, perfect. So I think it's better to consider whenever it is
Absolutely, yeah.
applicable, right?
Sometimes
Right.
you get some asymmetric loading from oblique angles, which would not be picked up
Hmm.
unless you allowed for that.
Right. Yeah. One more question, like how is BIM used in wind tunnel testing? So he's
Oh,
talking about building information modeling. So is there any application of building information modeling in the wind
so
tunnel?
far, no. So
Yeah.
far, no. BIM doesn't integrate with wind tunnel testing.
Yes. Yes.
Mm.
Yes. Okay. And one last question which we received, I think already you have answered it, but it was related to preparation of, say, the terms of reference or technical specifications for the wind tunnel testing.
Okay, we're happy to assist for no
Yeah.
extra cost to give
Yeah.
you a technical because, but if as a minimum, I would reference the AWES quality assurance manual. If you go to
Mm,
aws.org, you'll get a
mm,
free download. Or go
mm,
to our website. You can download it from our website. Go
mm,
to our blog, where there's a blog on this particular document. Um, you'll find it there as well.
mm, mm. Yeah, Bhushan is has put up one question that earthquake versus wind for Mumbai. Your idea. So, which is a governing force, whether earthquake or wind? Is there any opinion?
Um, I think a structural engineer would have a better say on this one, but from my experience,
Uh,
it seems to be the wind, even
yeah.
for 300 plus towers. Well, actually, maybe for the shorter, the very short ones, maybe, but I haven't figured out how short it needs to
Mm,
to be governed by earthquakes. So that's more is not my area of
yes.
expertise to answer this one.
Yeah.
Yeah.
Yeah. And it actually depends upon the height of the structure, geometry,
Yeah.
configuration. Yeah.
Obviously, the higher, the more it's going to be governed by wind.
Mm,
But I can't answer
mm.
this question. I think
Yeah.
you have to
Yeah.
speak.
Yeah.
Maybe Bhavin can. Maybe you can answer this one.
Yeah, yeah. So see, it
Mm.
actually depends upon so many factors. So, when we talk about earthquake versus wind, and that's why in our overall design philosophy, see, whatever structure is under consideration, we are considering both the forces. So, and then whichever is governing in the design, accordingly we proceed for the design. But when we talk about earthquake engineering, as Tony has rightly pointed out, our design philosophy is that we stress our structure beyond elastic limit. That is, we are going into the non-linear range. But when we talk about the wind engineering, we are limiting stresses beyond elastic limit. So that's a major difference between two major philosophy of the force. So even if my force value is similar, the overall design philosophy is extremely different. And that's why this is a common practice that we consider earthquake as well as wind in our model. And then there are different load combinations which we run. And then the member is designed for the critical load case or critical stresses, whichever higher force, whichever is a higher one, which is either generated from earthquake or wind load combination. Yeah, right. Okay, so it appears now that we have covered all questions from the audience. So if you still have any questions, you can still put it here, maybe within couple of minutes. Yeah. Meanwhile, it was an excellent presentation, and thank you all for raising such an interesting questions related to wind tunnel testing. And
Okay, your
yeah,
attention.
and as I see that wind tunnel testing is a very complex subject. So it was just only basic things which we could discuss in this presentation. Yeah. So the one more question is coming up. We can take one or two questions. Yash is asking that how does the three natural modes of seismic analysis in CSI ETABS helpful in the wind tunnel analysis? Okay,
Yeah.
what question is asking that let us say the structural model is created in ETABS and then dynamic analysis is performed, and from that the natural frequency is derived for the first, second, and third mode. Then how wind consultant will interpret that results or will be utilizing that data for wind tunnel testing?
Yeah. Okay, let me just make it. I'll have to go back to the sort of the design approach.
Okay.
The If you have set up your ETABS model for a seismic analysis, obviously the extent of cracking is more extensive than for wind. So just be careful with that, because what will happen is you'll give us natural frequencies which are perhaps a lot lower than they should be
Right.
if you had stayed within the elastic limit.
Mm-hmm.
So it's not necessarily the same dynamic properties as you would have for a seismic analysis. So just be careful with that.
Mm-hmm.
So you do account for some cracking for ultimate loads, but not to the same extent, I would say. I mean, I'm sure Bhavin can answer this question as well.
Yeah. So in as you rightly pointed out that there are stiffness modifiers which we have to enter for doing seismic analysis. So basically, we are considering a cracked section properties because the structure will be going beyond elastic limit. So there will be certain cracks which will be formed, and because of that, we cannot consider the 100% moment of inertia. So it's a reduced moment of inertia which we'll consider in a seismic analysis. So as you rightly told, it will become relatively flexible actually, and directly those values cannot be utilized because in the wind engineering we want to restrict our structure beyond elastic limits, so that there will be a substantial difference between the time period. So with this, I got one more question. Like so, do you define time period by yourself, or you ask the structural consultants to give the time period considering the elastic 100% elastic properties?
Yes, so yes, we rely on the structural engineer to
Okay.
either provide us his ETABS model and we can export from there, or they can export into a template, spreadsheet template that we can provide. So
Okay.
whichever they prefer.
Okay. Okay. So the closed interface is required for identifying the natural frequency, right?
Yeah.
Yeah, Bhushan has put up one more point that Reynolds number is a theoretical interpretation or has a real significance for our structures.
Oh yes, certainly. Your response, dynamic response of the building will be
Hmm.
a function of Reynolds number past a
Hmm.
certain point.
Hmm.
So especially when you have a circular or oval cross section,
Hmm.
very much so. And
Hmm.
you can get, if you are unlucky to have your natural frequency line up with the design wind speed, so that you could end up having a flutter situation much more easily than a square or sharp edge type of a profile. So
Hmm.
very, very, very important to be very mindful of the Reynolds number and reduce, because Reynolds number is also reduced to is related to the reduced velocity. Okay, so Reynolds number is also particularly important for facade cladding pressure studies because the flow regime around the building will change with Reynolds number, and if you are in a different flow regime, you'll have the reattached flow will come further into the downstream of the sides of the building, for example, and you can have a more extended zone of high negative pressure potentially. So that can affect also facade pressures. Right. Or flow, even the wind speeds, flow modeling around the building and pedestrian comfort will also be not so accurate.
Yeah, one question just from my side. Like, let's say as a structural engineer, how much time we should consider as for this total wind tunnel testing activities? Because all project, when we are at a planning stage, at that time this becomes a very important activity. So what may be the time duration?
It depends on how many towers are in the development. So for a single tower, it's 6 or 7 weeks, and then it will increase from there. It's not proportional, but there'll be some increase with more towers, of course.
Right. Okay.
But we do give you a desktop estimate within the first 1 or 2 weeks, just so we're on the same page. It sort of minimizes the amount of rework to the structural model once you have the results. So it becomes usually just a checking exercise, hopefully.
Right. Okay, so now the people are appreciating the session. Raksha Bhatia is telling, thank you for the nice session. Yeah. Yes.
You're welcome. Yeah,
most welcome.
It's always good to speak to you guys.
Yes. Dr.
Thanks.
Rajesh is telling,
thanks everyone.
Yeah. Okay, Yash Patel is appreciating. Thank you, Yash.
Thanks everyone.
Yeah, thank you everyone. Okay, so thank you, Tony, for sharing
your. Thanks, Bob.
Yeah.
Okay. All right. Okay.
Okay. Bye. Bye from our side. Yeah.
Bye.